In nature, we can find all sorts of physical manifestations of cosine waves. For example, the vibration of a spring that is subtended upon a ceiling, or for example, the vibration, the way how an electron vibrates at an atomic scale inside an atom. So those kinds of things represent the beauty of mathematics when we are talking about uh, trigonometric function, particularly the cosine function. So in this video, FB6, as well as my classmates are going to discuss the different properties of the parent cosine function, as well as the different ways to manipulate and transform it in order for us to graph transformed cosine functions. Displayed on the screen are our objectives for this session. Throughout the presentation, the viewer must be able to illustrate the graph of the parent cosine function on a rectangular coordinate plane, apply the rules of function transformation in graphing cosine functions of form A times cosine of B quantity B times quantity X minus C plus D, and solve problems involving graphing cosine functions. Before we proceed any further, let us first define terms that are commonly or frequently used when we are talking about cosine functions. In mathematics, we have what we call the analytical process transformation. It is the act of translating, rotating, reflecting, or dilating a given shape or function in a coordinate plane. When we are to transform a shape or graph, take note that the identity of that specific function is retained even though its properties are manipulated. Why is that so? Because transformed functions are dependent upon their parent functions. A parent function is a function without any transformation. It is the simplest form of a function among a family of the same type of functions. Therefore, its property serves as the basis for every other graphs of a certain function given different arguments or inputs. To illustrate the idea of transformation, in the screen we have the figures of manipulated into sorts of different ways. Um, First, we have translation, which is the act of moving an object from one place to another. So as we can see here, look at my cursor, the object is moved from here into there. When we reflect an object, we tend to inverse its property or mirror its properties by an axis or a point, depending on its symmetry. Like for example, cosine function is symmetric by the y-axis, so therefore if we reflect it by the y-axis, there would be no change happening. When we are rotating, we tend to change the orientation of an object. So as we can see here, B was on top on the original setup, B was on top, while on the other hand, C was on top. For the dilation, it is the act of enlarging, stretching, uh, and shrinking, even shrinking of a given figure. So what's common among these figures? Even though we have manipulated its properties, we can see here that the identity is maintained or sustained. Even though we moved it or reflected it, rotated it, or dilated it, stretched, shrinked, um it's still a triangle, right? So that's the principle of transformation, and that also applies to the concept of, in mathematical analysis, which studies the trends of mathematical functions, just like the cosine function. Furthermore, so from our definition, parent functions are the simplest form of a function across a set of a type of function. So what we have here in our screen is the parent functions in algebra. So parent functions have these unique properties or behaviors rather that can be generalized among its transform functions. That's why functions are dependent upon these types of functions. So for example, we have uh, the constant function. All constant functions are graphed as horizontal lines. Linear functions, of course, from the name itself, are lines with slopes. On the other hand, the absolute value function has this iconic V-shaped graph, no? And so on and so forth. Each have their own behaviors. So, what we are trying to do is to uh, use those common general behaviors and transform them such that we can form other functions, other transform functions uh, that is inputted that is given different arguments. So of course we have our parent functions in trigonometry too, such as the parent function of sine, cosine, tangent, cotangent, secant, and cosecant. But for this presentation, we are only going to focus on discussing the cosine function. Without any further ado, let us now discuss the properties and the graph of the parent cosine function. By convention, a cosine function is a function that can be written in the form f of x is equal to a times cosine of quantity b times quantity x minus c plus d, where a is the amplitude, b is related to period, p is equals to 2 pi divided by the absolute value of b, c is the horizontal shift, and d is the vertical shift of the graph of the function in a rectangular coordinate system for all values of c, d, and x that are real numbers, and a and b is any real number that is not equal to 0. Take note that a must not be equal to 0. Why? That is to sustain or retain the identity of the function, because if we are to make a 0, then this whole term will become 0, and the new function will just be f of x is equal to d, which is now a constant function and no longer a cosine function. Additionally, b must not be equal to 0 so that our period will not be um, undefined. If we want to make the argument of cosine here, the b times quantity x minus c, if we want to make that argument to be 0, it is the value of x minus c that we must change. Continuing, the parent cosine function is a function f of x such that f of x is equal to cosine of x for all real number x. In other words, the parent cosine function has a is equal to b is equal to 1 and c is equal to d is equal to 0 in its conventional form. This setup yields graph behaviors common to any transformed cosine functions. That is why we are gonna use its properties in order for us to determine, let's say, the period or the trends, the changes in the amplitude of the of the transformed cosine functions. So given that a is equal to b is equal to 1 and c is equal to d is equal to 0 in our parent cosine function, there is no translation because there's no horizontal or phase shift nor vertical shift that happen. Therefore, the midline will stay situated at y is equals to 0. There is also no dilation, no stretch, or no shrink in any direction. Therefore, the amplitude will uh, stay stay being 1 unit and the period to be 2 pi. The natural innate the innate or natural domain of any cosine function is all real numbers ranging from negative infinity to infinity, and uh, a non-change or untransformed function cosine function has range from -1 inclusive up to 1 inclusive. An analogy that I can make for you to better understand what I mean by transforming the parent cosine function is that the cosine transforming cosine function is like molding your modeling clay. Have you ever played with modeling clay? So when you play with modeling clay, you can stretch it or compress it, squeeze it in all sorts of forms, and you can even accumulate it for it to grow in size or divide it into little pieces. That's what we can do to cosine functions when we are transforming it. We can stretch the cosine function, we can shrink the cosine function horizontally, vertically, and we can even make it grow or shrink in size. And even, but even when we are transforming it, the clay, um, when we are molding a clay, the clay stays the same being clay. So that's also the point of the retention of the identity. When we transform a cosine function, it retains its identity. Therefore, its behaviors, the behavior of the parent cosine function can be applied to the transformed parent functions. So what are those behaviors? Since a is equal to b is equals to 1, this provides flexibility for the function to dilate depending on the factors a and b. So it can grow by the factor a vertically, or it can shrink depending on its value, as well as horizontally, which is dependent on the value of b. On the other hand, since c is equal to d is equal to 0, these variables allows you to locate the midline and the minima and maxima, or the minimum and maximum values of the function. That allows you to that helps you in graphing cosine functions, as well as its counterpart na sine function. So here we can with this, just like a clay, the parent cosine function can be manipulated to yield graphs of varying shapes. So without any further ado, here are the properties of a transformed cosine function. If we take a quick look, it's resembling the properties of the parent cosine function. It has a midline, it has an amplitude, and it has a period. Um, if you might notice, it also inherited the behavior of having a wave-like pattern. So that's the identity I was talking about when we talk about transformation of functions. The transformed function inherits the notable characteristics of their parent function. Now, given that a and b are values not equal to 0 and 1, and c and d are values not equal to 0, we will observe a translation, specifically a phase shift, brought upon by the value of c, and vertical shift by the value of d. Since there is a movement of up or down of our function, so its midline will move up or down as well. So therefore, our midline will be located at y is equals to d. Now, there will also be there will also be um, dilation, vertical dilation brought upon by the value of a, and horizontal dilation brought upon by the value of b. Since there is a stretching and shrinking that will be happening, the amplitude will change according to the value of a, absolute value of a, and the period will extend or compress depending on the value of b. Though there are some changes, even though there might be some changes horizontally, let's say we stretch the graph, or compress the graph, it still extends from the value of x that we can input into our function, still extend from the negative infinity up to positive infinity. But now the range has changed to negative of the absolute value of a plus d up to the absolute value of a plus d, both in both inclusive. So with transform cosine function being a clay, it inherited the periodic nature of the parent function, the wave-like pattern, the domain extending to positive and negative infinity, as well as the having a definite range only extending to a certain distance from the midline. So that's what we meant by retention of the identity. Please take note of the important features of the transformed cosine function, the midline, the amplitude, and the period, as this will be useful when we're graphing transformed cosines, which we'll discuss later in this video. To give you an example, this graph let me get my pointer. This graph right here is an example of transformed cosine function that underwent dilation. Another example is the one right here. So as you can see, it's stretched horizontally and shrunk vertically. And yet another example, another type of transformation. So here we have translated the graph of our parent cosine function. We moved it from its original position to another. So what have caused the dilation and the translation in the sample graphs I have presented? That's what we will know as my classmates discuss to you what the effects of A, B, C, and D by themselves do to the graph of the cosine function. But before that, let me ask you a few questions. So for you to for us to evaluate if you really understood what we have discussed so far. So to better amplify your understanding of the form of the cosine function, here are some questions to ponder of. In the form of cosine function a times cosine of quantity b times quantity x minus c plus d, why is it a is not equal to 0 and b is not equal to 0? Feel free to pause the video and contemplate for your response and come right back for the answer. A is not equal to 0 in order to maintain the identity of the function. If A is not if A is equal to 0, then it will become a constant function of form y equals t and no longer a cosine function, just like what I've said earlier. Now, b is not equals to 0, so that the period 2 pi divided by the absolute value of b will not be undefined. If you want to make the argument of cosine to be 0, then it must be the quantity x minus c that you change the value of. That's very great. You're now familiar with the conventional or standard form of the equation of a transformed cosine function. Now, going back to the examples presented earlier of the dilated and the translated cosine functions, what's the reason behind them? Why did the graph of the function moved or grew, grew or shrunk in size? What effects do the variable a, b, c, and d bring upon our parent cosine function?
Have you ever wondered what happens to the graph of a function, specifically a cosine function, if we manipulate its values? If so, good day and mabuhay. Our group is here to serve you. I am FG3 Marion Galimlim together with the Group 2 members and We will discuss what will happen if we manipulate the values of A, B, C, D, A and B, and A, B, C, D of a cosine function, and identify the new graph's amplitude, period, vertical shift, and horizontal shift. Remember that the formula for our function is y is equal to a cosine b times the quantity x minus c plus d. Now, focusing on the cosine function, the equation of our mother graph is f of x is equal to cosine x. Let us now proceed with manipulating the value of a. The a in the function represents the amplitude of the graph, where its value determines the vertical shrinking or stretching of the graph. Amplitude also refers to the height from the center line to the peak. To get the amplitude, we must get the absolute value of a. In the function we have here, f of x is equal to 3 cosine x. This is the new graph's function. In this case, a is equal to 3 and amplitude is the absolute value of 3, which is equal to 3. Comparing it to the mother graph, we can take a look at the picture right here. The red line represents the mother graph and the blue line represents the new graph where we manipulated the value of a with 3 cosine x. Comparing the two, it can be seen that the new graph is taller than the mother graph. It is because the mother graph has an amplitude of 1 where the function oscillates between -1 and 1, while the new graph has an amplitude of 3 where the function oscillates between -3 and 3. All in all, from the graph, the peaks are higher and lower in 3 cosine x compared to cosine x due to the increase in amplitude. And that's what happens when we manipulate the value of a in a cosine function. Let us now move on and find out what will happen if we manipulate the value of b. Take it away!
Thank you, Marian, for that wonderful explanation. Now, let's move on to the next segment of the video. I am FG for Charming Kalweng, and I am here to discuss the effect of changing the value of b in our mother graph f of x equals cosine f. The graph of cosine function is given by f of x equals a cosine b quantity x minus c plus d, where b influences the period and its value determines the horizontal shrinking or stretching of the graph. But first, what is a period? The distance on the graph between two repeating points is called the period. The formula for the period is given as t equals 2 pi over absolute value of b. The value of b represents the frequency or number of cycles completed by the graph in a range of 0 to 2 pi. Do take note that the graph displays a horizontal stretching when the value of b is greater than 0 but less than 1. When this happens, the function's period is bigger than 2 pi. However, the graph will exhibit a horizontal shrinking when b is greater than 1, indicating that the function's period is smaller than 2 pi. Let's graph the standard cosine function f of x equals cosine x as our first example. The value of b in this equation is 1, resulting in a period of 2 pi when evaluated in the given period formula. This suggests that there is a one cycle seen in 0 to 2 pi intervals in both directions, as seen in the graph. Now, let's see what happens when we change the value of b. Consider the function f of x equals cosine 4x. Here, the value of b is equal to 4. When we substitute it to the given formula of the period, we will get a period of pi over 2. This suggests that there are 4 cycles seen in 0 to 2 pi intervals in both directions. The period is smaller than usual when we compare this function to our mother graph, which is f of x equals cosine x. This is because the value of our b is greater than 1, which then results in a smaller period. Thus, the function of f of x equals cosine 4x has a shrinkage or accelerated period compared to the standard cosine function f of x equals cosine x. When the period of a function shrinks, it means that it takes less input of x values for the function to complete one full oscillation. And that is how we can determine how changing the value of b impacts the graph's period, frequency, and horizontal stretching or shrinking. Let's now move on to the next part of the video.
Thank you, Charmaine, for explaining what happens when you change the value of b. Now I, Adrian James Cruz, FB4, will explain what happens to the mother graph when you change the value of c. With our mother graph function as f of x is equals to cosine x, our new function would be f of x is equals to cosine x plus pi. In the picture shown, our mother function is represented by the red line while the blue line represents our new function. As you can see, there is not much change in the graph. This is because we didn't change the value of a or b at all. As we know from the previous explanations, a determines the amplitude and b determines the period. Since there is no change in the value of both a and b, the new function won't get wider or thinner. So, what is the change? As you can see, the positions of the graphs are different. This is because the variable c represents the phase shift of the graph. Whenever you change the value of c, the graph will either move left or right. If c is positive, it will move to the right, but if it's negative, to the left. The value of our c is negative since the graph of a cosine function is f of x is equals to a cosine b times x minus c plus d. So, the value of our c is negative pi. Since the value of c is negative pi, the graph moved to the left by the amount of pi units. In summary, the change in the value of c determines the phase shift of the graph. When the value of c is positive, the graph moves to the right, but the value of c is negative, the graph moves to the left. In my example, the graph moved to the left by the amount of pi units.
Change in the value of d. Thank you for explaining the change in c, Adrian. Let's now move on to the change in the value of d. I'm Ethan Cuesta, FP5, and I will be observing the graph of a cosine function with a change in the value of d. With our mother function as f of x equals cos x, our new function would be f of x equals cos x plus 5. The red line represents the mother function, while the blue line represents f of x equals cos x plus 5. Observing the graphs, we can see that there is not much change to the graph of the new function in comparison to the mother function. The new function did not get wider or thinner. It only seemed to move up. Why did the new function move up? Let us look into it. Because there is no change in the value of a, the amplitude of the new graph will be the same as the mother graph, being 1. There is also no change in b, which makes its value as 1. With b equals 1, the period of the new function will also be 2 pi, same as the mother function. With no change in the amplitude nor period, there is no change in the stretching of the new graph at all. This explains why the new function did not get wider or thinner and had the same stretching as the mother graph. Moving on, we have the phase shift. The phase shift is represented by the variable c. Since there is no change in c, its value is 0. Thus, the new graph has no horizontal shifting. Lastly, we have the vertical shift. The vertical shift is represented by the variable d. The value of d is 5. Since d is positive, the graph moves upward. Thus, because d equals 5, the new function shifted 5 units up in comparison to the mother graph. In conclusion, the change in the value of d determines the vertical shift of a graph. If the value of d is positive, the graph shifts up. If the value of d is negative, the graph shifts down. As for my example, the graph of the new function shifted 5 units up in comparison to the mother graph.
Thank you for those informative presentations. Now, I wonder, and maybe you're even wondering, what if we apply changes in A or B, or A and B, and A, B, and C, or and D all together? What will happen to the graph of the parent function? What kinds of transformation will occur when these changes happen simultaneously? That's what me and FB18 will discuss.
Very nice presentation indeed, Ethan. I hope you viewers have been on the edge of your seats lately because I'll be your guide for this lesson. Mabuhay and good day. You can refer to me as FB18 John Joaquin Portillo or FB18 for short. And in this lesson specifically, we'll focus on understanding variables A and B. With the introduction out of the way, Shall we begin? Great, let's go! But first, how about a quick refresher game? It's a short 3-question quiz. Nothing more, nothing less. I'll give you 5 seconds to answer. Don't worry, these questions come from earlier lessons. I'll also provide some choices, just to make things easier. If you're stuck, pause the video and take your time. You have nothing to lose in this game, so it's natural to take a break once in a while. Are you up to the challenge? Here is your first question. Question 1. If you were to graph a cosine function, what is the general formula? Your options are A. Y equals A cosine B times the quantity x plus c plus d. B. Y equals A cosine B times the quantity x minus c minus d. C. Y equals A cosine B times the quantity x plus c minus d. Or D. Y equals A cosine B times the quantity x minus c plus d. Remember, you only got 5 seconds, starting now. Timer's up. The correct answer is D. Y equals A cosine B times the quantity x minus c plus d. Well done. Moving on. Question 2. In the general formula, what property determines the vertical shrinking or stretching of the graph? Your options are A. Amplitude, B. Period, C. Phase shift, D. Vertical shift. 5 seconds, starting now. Timer's up. The correct answer is A. Amplitude. Great job! Just one more to go. Question 3. Fill in the blank. A blank is called the distance on the graph function between two corresponding points. Your options are A. Amplitude, B. Period, C. Phase shift, D. Vertical shift. The timer begins right now. Timer's up. The correct answer is B. Period. Nice one. We completed the quiz. All 3 questions that you saw previously are especially relevant to our lesson today as we delve into 2 variables instead of the usual one. Let's explore the potential impact of altering variables A and B. Imagine the new graph in blue represented by the equation y equals 2 cosine 2 times x or y equals 2 cosine 2x. To guide our discussion, let's address these key questions. 1. What changed? What alterations occurred? 2. How do you graph y equals 2 cosine 2 times x if you start from the mother graph? 3. How does this change in variables affect the properties of the mother graph? It's evident that variables a and b are the ones that underwent modifications in value. But that still begs the question, what implications do these alterations carry? This prompts a deeper investigation of their actual significance. With the amplitude adjusted from 1 to 2, several remarkable shifts emerge. Observe the graphical representation. Both minimum and maximum points stretch vertically at the same time, allowing the highest peak to reach y equals 2 and the lowest point of the cosine function to reach y equals minus 2. However, it's crucial to note that no alterations occur in the remaining properties. This consistency arises from the fact that the values of b, c, or d remains unaffected by this amplitude adjustment. In other words, the period is still 2 pi and the new graph did not change position. Starting from the red graph of the previous slide, with the value of b now set as positive 2, reveals an unaltered amplitude. However, this shift in the value of b impacts the period. Conventionally, the formula to calculate a cosine function's period remains the same. It's 2 pi divided by the absolute value of b. Plugging positive 2 into our given formula yields a period of pi. Consequently, because the value of b surpasses 1, the period undergoes horizontal shrinking. Similar to the amplitude, the remaining properties of the graph remain constant despite this change in value. To recap, adjusting the values of a and b to positive 2 has resulted in a shift in the graph's amplitude and period. Initially, at 1 unit, the amplitude has now doubled to 2. Concurrently, the graph's period, initially spanning 2 pi, has condensed to pi due to the value of b becoming 2. Thus, these mere adjustments induced vertical stretching and horizontal shrinking simultaneously without any phase or vertical shifts occurring, as both c and d values remain constant. And that is all the time we have, folks. Coming up next, we end this video off with the final lesson led by FB6 Mark Angelo de Gracia. Once again, this is FB18 John Joaquin Portillo signing off.
Now, what if there are changes in A, B, C, and D all together? So let us dissect what will happen when we do so in transforming a cosine function. So given that we have 4, we have the function 4, f of x is equal to 4 times cosine of quantity 1 half times quantity x minus pi over 2 over all plus 3. We must find the transformations made by each of the changes in the values of a, b, c, and d. So let us dissect what will happen in each transformation and accumulate it all together for us to arrive from the parent function into the transformed function. So first we have, let us apply it lexicographically or alphabetically. So it goes from A, B, C, D. So first applying the transformation made by A, since A is equal to 4 and 4 is greater than 1, then we must observe a vertical stretch in the graph, just like what we see here. And then when we apply B along with A, since our B is equals to 1 half and it is between 0 and 1, um, we will get a horizontal stretch according to the rules discussed earlier. And after that, if we uh, if we transform again by applying C, we will get this curve right here that is parallel to the that is parallel to the transformed function. That is true. That applies true for all functions that have transformations with their a value of a, b, and c. So we're so close now. By just adding 3, which moves the graph upwards towards the transform function, we have now arrived to the target graph that we are aiming for. So to summarize the properties of the transformed function, given that a is equal to 4, b is equals to 1 half, c is equal to pi over 2, and d is equals to 3, um, the translation that we have observed is that the parent function moved pi over 2 units to the right and 3 units upward. So therefore, its midline will be at y is equal to d or y is equals to 3. And we have also observed dilation. There is a vertical stretch by a factor of 4 and horizontal stretch by a factor of 2 because the period doubled. Therefore, the amplitude must be 4 units, etong A, and the period must be 4 pi, the distance between the two corresponding points, such as the crest or the minimum points here. Given all that, find the domain of our function is still all real numbers, since there is no restriction after all, and the range went from negative 1 inclusive to 1 inclusive. It became negative 1 inclusive up to 7 inclusive. In conclusion, when changes in A, B, C, and D occurs at the same time, dilation and translation is applied simultaneously to the graph of the parent function f of x is equal to cosine of x, given that a and b are real values other than 1 and c and d are real values other than 0. To summarize the idea of transformation in cosine functions, please read the following text. Again, to check your understanding of our discussion, here are some questions to ponder regarding the rules of transformation. In the form of cosine function a times cosine of quantity b times quantity x minus c over all plus d, um, why is it x x minus c instead of x plus c, and why is it plus d instead of minus d? So the explanation to those, for the first number, it is x minus c rather than x plus c to compensate change in the argument of the cosine function due to horizontal shifts. Say we translated the parent cosine function, then we can imagine that we move the whole picture c units from the original position, including the x and y axis. If we look at the new perspective, the new axis is the representative of the x equals to 0. Now, to retain the equality to 0, we must subtract values of c instead of adding. Now, for you to get it better, let us use logic. Let us apply logic here. So as we can see here, look at the cursor, the laser point. The point here has the same ordinate or y value as this point here. Now for them, that is those are points 0, 1, and 2, 1. Now they both have different abscissas or x values, but they both have the same y values or the output of the cosine function. So what can we do to make them equal to one another when inputted in when given as argument in our cosine function? Therefore, then we must subtract uh, the amount of which we translated the function for us to retain or to make the equality true. So for the second one, we have y is equals to a times cosine of quantity b times quantity x minus c over all plus d. It can be rewritten as y minus d times the equal to times cosine of quantity b times quantity x minus c. This form of the equation follows the counterintuitive nature of x minus c. So there are both subtractions now, y minus d and x minus d. The d was transposed to the right hand side of the equation to isolate y or f of x. That is why it is plus in our conventional form. Given everything that we have learned in transforming cosine function, let us now discuss and apply what we have learned in graphing the transformed cosine function in a rectangular coordinate plane. Here are the suggested steps in graphing a cosine function in a rectangular coordinate plane. First, you must check if the given function is written in conventional form. If not, then rewrite it for us to know and identify the values of a, b, c, and d. Then we must list their transformation effects. We must draw the midline y is equals to d, so that will be our basis for the rest of the graph. Starting at x is equals to c, we must draw points cycling in order. So these are the points you can just substitute or use your intuition in graphing when you are graphing manually. And then across those points, you must sketch a smooth periodic curve passing through the plotted points. So, and then lastly, you must expand the graph in the given interval in the problem, then label the graphs and its properties, then box your final graph. So that the labeling and the labeling is important so that the viewer of your work, let's say your teacher checking your paper, would easily understand what's going on with your output. For our first example, graph the function f of x is equals to 3 times cosine of quantity 2 times quantity x minus pi over all plus 4 for all values of x that are real numbers. So given the function, we must find we must graph the function for all real numbers. Since it's already in conventional form, we can skip step one. Then we must list out the values of a, b, c, and d. So from here we have a is equals to 3, b is equals to 2, c is equals to pi, and 4 is equals d is equals to 4. So what do this mean? Do these values mean? A is equals to 3 means that the parent function will vertically stretch by a factor of 3 and the amplitude is 3. B is equals to means that there is a horizontal shrink by a factor of 2 and our period becomes pi instead. C equals pi means that there is a rightward shift by pi units, and we will start plotting the points at x is equals to pi. And D is equals to 4 means that there is an upward shift by 4 units and the midline is at y is equals to 4. So continuing, here we draw the midline and then we plot the points according to the formula, or you can use your intuition. And then we sketch a smooth curve across these points, and then we expand the graph according to the given interval. So in this case, we have for all real number x. That's why it's extending in both sides. And here are the labels. In the labeling, we have the name of the function, the equation of the function, the domain, the range, the amplitude, the midline, as well as the period. So I'm not gonna discuss the other examples any further as much as I did in this one. But hopefully you understood what I meant with this one by this example. So now for this example, we have a limited interval now here. So even though it seems like it is written in uh, a conventional form, it is not. Kasi look at here, it is plus and this is minus. When we expect it, we expect it to be x minus c and plus d. So when we rewrite it that way, we will have this equation right here. So here are the implications. You can read them. So we draw the midline, we plot the points, we sketch a smooth curve, then expand according to the given interval, and then we label the graph. We do the same for the third example, except this one. Uh, Mark, I thought FB6, I thought we're only gonna discuss about, I don't know, sine functions, cosine functions. Why is there's sine function in here? So don't worry. We can use different trigonometric identities in uh, deriving a cosine function. So by the difference identity for cosine, uh, This expression right here is equals to cosine of x minus quantity x minus pi over 2. Hence, we can equate negative 2y plus 5 all over 7 to cosine of quantity x minus pi over 2 and derive the conventional form. Take note, just be careful when we use trigonometric identities when we are deriving a certain type of function because not all identities share the same domain and range. Take note that functions are only equal if their domain and range are equal are the same, congruent to one another. Moving on, here are the our list of A, B, C, and D, its implications, and the important parts of our graph. We draw the midline, we plot the points, we sketch the smooth curve, and we expand it according to the given interval, and we label the graph. That is all for this presentation. We hope that we hope that you have learned something new and enjoyed this discussion with us. If you have any queries, you can put them down in the comment section, or if you want to post your answers for checking, manual checking, or some tips, you can ask us in the chat comment section below. Don't forget to share it to your friends. That would be of great help to us. Thank you.